Good morning, welcome to new lecture. Today I will continue with slope deflection method. If you remember, let's review what we had. If we have one structural member, initially it is straight one member, is subjected to external load. After deformation, we will have deformation something like this. We will have bending moment here at this point A, this point B. MA will be bending moment at joint A, and we will have here theta A. The bending moment at point B will be MB, and rotation or slope here will be theta B, and joint A respect to the B, they will have a distance which is perpendicular to the initial direction of the AB. In general case, we call that delta, lateral deflection. The initial length is L, EI is constant. If you remember, with superposition, I divided this system to 4 simple system. One of them was two end fixed, subjected to external load such as Q. So we can find in both end reaction, and we call that MA1, MB1. Then I can apply the effect of rotation at joint A. So only I will apply that effect. So I will have here MA2, and I will have here theta A, and I find the relationship between MA2 and theta A. If you remember, it was 4EI over L theta A. In that case, reaction in other side will be half of that. It will be MB2, which is half of MA2, and that will be 2EI over L theta A. Plus, if I apply the effect of rotation at joint B, that will be another one end pin, another end fixed support system. This will be MB3. This will be theta B here. Again, MB3 will be 4EI over L theta B. So if we apply this moment here, it will be half of that. That will be MA3. That will be 2EI over L theta B. And the effect of lateral deflection or settlement, I calculated, and you see in one point, because it is symmetrical, that point it will be exactly in the middle. If total settlement of A respect to the B, it was delta, at the middle that will be delta over 2, and we will have inflection point at the middle. So moment here is equal to 0 because curvature is here to the 0 before that, and after that the curvature direction will change. So at that point curvature is 0, that means internal moment at that point is equal to 0, and using the property of the inflection point, I find moment here because of the support settlement or lateral deflection. And if you remember, that was 6EI delta over L square MB4, and here MA4, it was 6EI delta over L square. And you see here the curvature, it is convex shape, here concave shape. So at the middle there is no curvature, or radius of curvature goes to infinity. It is a straight line. Moment there is equal to 0. So entire MA from superposition here, MA will be equal to MA1 plus MA2 plus MA3 plus MA4, and MB will be MB1, this is MB1, sorry, MB2, MB3, MB4, because if we add these four systems, we will get initial structural elements. So from here, I can write MA is equal to MA1 plus MA2 plus MA3 plus MA4, and MB will be MB1 plus MB2 plus MB3 plus MB4. We have the magnitude of each one in terms of theta and delta. Theta is kind of deformation or displacement. So we have here in terms of theta, here delta it is lateral deflection, so it is kind of displacement. For that reason we call this method, it is displacement method, because we find the relation between moment and displacement in the form of rotation theta and lateral deflection delta. So MA1 and MB1, it is because of external load. MB2, MB2, it is because of rotation at node A. 3 because of rotation at node B, and 4 it is because of lateral deflection. If I substitute this, I will find the final slope deflection formula or equation. Slope deflection equation, if I add those, I will end up finally, I can write MAB, M for AB it means MA is equal to M fix AB. I will find that is we assume both end is fixed and only we have external load. We can find the moment for support using force method. Before a lot of researchers, they found it and they developed table. We will use those tables, but you can find yourself too. So M fix AB means the support moment because of external load whenever we assume both end is fixed, plus 2EI over L minus 2 theta A minus theta B plus 3 delta over L, and MBA will be equal to M fixed BA plus 2EI over L minus 2 theta B minus theta A plus 3 delta over L. We apply this formula, and if I want to summarize the procedure for slope deflection method, I can write in 4-6 steps. I summarize everything here. If we want to solve indeterminate structure using slope deflection method, what is the procedure? So I call it application of slope deflection method. How I will apply? First, I will identify all kinematic degrees of freedom to see how many equations, how many unknowns we will have. That depends on degree of freedom. Second, determine the fixed end moments at each end of span to applied loads. It means fixed end moment, and we will find those using tables. 3. Express all internal moments in terms of slope, deflection equations. 4. Write down all equilibrium equations. With different examples I will solve, I will clarify this step, don't worry about that. 5. Solve the above set of equations for joint rotations and displacement. And finally, step number 6, determine all rotations and displacement. After we find all rotation and displacement, we will plug in the slope deflection method, formalize slope deflection equations, and we will find moments. I will clarify these steps using several examples. Don't worry, you will understand, because I will solve different problems using the slope deflection method, and you will see how we can apply these steps in real problems. First, very simple example. Assume we have one beam, one end is fixed, another end is roller. This beam is subjected to concentrated load at mid-span, and the length for span is, total length is L, each side is L over 2, because load it is at mid-span. Problem statement says this support A, B. Support B settles. We have settlement at support B equal to the delta. And if we have this system subjected to concentrated load at mid-span and settlement delta at B, what is moment at support A? We want to find this. Let's look at the slope deflection equation. First, if we look at the fixed end support tables, if we have beam, two end fixed support, and we have concentrated load at mid-span, and the length is L, support reaction will be PL over 8, PL over 8. You can find that using tables or using force method, you can find that this is something we know that. Now let's write slope deflection formula. MAB is equal to M fix AB plus 2EI over L minus 2 theta A minus theta B. Let's see, settlement at point B. After settlement, this beam will rotate clockwise. If it rotates clockwise, we will plug delta negative. So it will be negative delta 3 delta over L. If settlement cause rotation clockwise, our assumption it is negative delta. If it cause rotation counterclockwise, we will plug positive. So this is MAB. In this equation, let's I substitute MAB will be equal to M fix AB, this one, M fix AB. You see the reaction, it is counterclockwise, so positive PL over 8 plus 2EI over L minus 2 theta A minus theta B minus 3 delta over L. Theta A, rotation as support A. Rotation here, because it is fixed support, it is 0. So we know this term is 0. From here, this will be PL over 8 minus 2EI theta B over L minus 6EI delta L squared. Let's look at today MBA. MBA will be M fixed BA plus 2EI over L minus 2 theta B minus theta A. Again, settlement will cause this beam will rotate clockwise, so minus 3 delta over L. From here, M fix BA, it is clockwise, so negative PL over 8. Okay. Theta A, again it is 0 minus 4EI theta B over L minus 6EI delta over L squared. Okay, what is MBA? MBA moment here, this moment at point B, because it is hinge moment there, it is equal to 0. So I can plug this one is equal to 0. If I plug that one is equal to 0, I can find minus 4EI theta B. This term minus 4EI theta B over L equal to, if I take this to other side, will be positive 6EI delta over L squared. Because this is negative, we'll go to other side, it will be positive. This will be positive 2 plus PL over 8. If I plug that here, you see here we have negative 2EI theta B over L. Here negative 4. So if I want to convert this to the 2, I will multiply to half. So I should multiply this to half, both sides. In that case, this will be negative 2 ei theta b over L. Negative 2 ei theta b over L. I can plug this term instead of this. So let's continue here. MAB will be equal to PL over 8. Instead of this term, I will plug this term because they are equal. Plus 6EI delta over 2L squared plus PL over 16. PL over 16. From here, I can find MAB will be equal to PL over 8 plus PL over 16 will be 3PL over 16 plus 6, sorry I dropped this term here, I should write this here, 2 minus 6EI delta over L squared, because instead of minus 2EI theta b over L, this term, I plug this one, so PL over 8 plus PL over 16 will be 3PL over 16. This minus this will be, let's see, everything is right or we have mistake over there, let's see. This will be P, okay. This will be 6 over 2, so this will be 3EI delta over L squared minus 6EI. So this will be negative 3EI delta over L squared. Again, double check to see everything is right. I didn't make any mistake. Let's see. For some reason, the solution I did it before, I find is positive. Let's see, everything is right here. So, negative, this will be positive, this will be positive. So, if we plug here, that is negative, positive, positive. It seems right, but again double check, maybe I made one mistake, negative, positive. But it will be something like that. Okay, let's recap to next example. Next example is very simple example. We have this system 2L L over 2, L over 2. Here we have concentrated load P. Here we have load P over 2. A, B, C, D, here is subjected to distributed load. The intensity of load, it is W. Problem statement says find P, this P, so that ME is equal to the 0. We want to make ME moment here is equal to 0. How much is the P in terms of L and W? Okay, if we want to make it ME is equal to 0, because there is no external load on this column, there is no external load in the BE part. In order to make moment here is equal to 0, if I make rotation at point B is equal to 0, so no rotation at B means moment at E is equal to 0, because from slope deflection we know MED, moment at point E, is equal to M fix ED plus 2EI over L. 2EI over L, here it is the length of column, it is 3L, minus 2 theta E minus theta B, because there is no lateral deflection here. This point B cannot move respect to point E in vertical direction. That delta term is equal to 0. So this is equal to ME, moment at support E. M fix ED, M fix ED. It means fixed end moment because of external load. There is no external load on this column, so this term is equal to 0. Theta E, because point E is fixed support, so there is no rotation. This term is 0. Now, if theta B is equal to 0, in that case ME will be equal to 0. How we can make theta B is equal to 0? Theta B equal to 0 means this part of the beam will not rotate. It is like fixed. So if I separate AB part, this is external load. This is 2L AB, and no rotation at point B, it will convert this part to the fixed support. If we have beam, both support is fixed and the length of beam is L, subjected to distributed load, uniform distributed load. From table, we know, of course, we can calculate from force method too. The support reaction will be W, intensity of the load, times L squared over 12. Here in this example, so the support reaction here, it will be W, the intensity of the load, times L squared. L, it is 2L, 2L squared over 12. This will be W, L squared divided by 3, because our L, it is 2L. It will be 4, 4 and 12, they will cancel. Here we will have 3. So this is support reaction at point B. So if I want to make this fixed, the amount of moment I need to apply here, it is W, L squared over 3. Or if I look at to the E, B column, the action, not reaction, the action will be the same magnitude in inverse direction. This distributed load, if I prevent rotation at point B, will apply moment as much as W, L squared over 3. How much moment this load will apply to another side. Okay, that moment will be, if we put P here in the middle of CD part, because this is in the middle of CD part, half will transfer to point D, half will transfer to point C. So the contribution of C part from this load will be P over 2. P over 2 will come to this hinge because of this load downward. Okay, so P over 2 downward. Extra load we have here, that is P over 2 as well. So P over 2 plus P over 2 from this load, it will be P. So let's see, I can remove this part. I will add another P over 2 here. P over 2, P over 2. So entire load downward here will be P. P times L will be moment from this side, right side of this structure. If these two moments, they are equal, if the magnitude are equal, because they are in inverse direction, they will cancel out each other. So there is no rotation at point B. In that case, we should write W L squared over 3 should be equal to the PL. From here, P will be equal to WL over 3. So if we choose in this structure initial shape P over 2, P over 2. If I choose the magnitude of the P is equal to W, this W times L over 3, we will not have any rotation at joint B, and moment reaction at support E will be equal to 0. Let's look at one more example. Then next session, again I will solve several examples using the slope deflection method. One more example is very simple. Symmetrical structure. Six feet, 4 feet, 4 feet. EI is constant, and we have here at midspan 8 kips load, and here again another 8 kips. A, B, C, D. We want to find M, A, support traction A. How many degree of freedom we have here? How many nodes we have? 1, 2, 3, 4 nodes we have. But 3 nodes out of these 4 nodes we attach using fixed support to the ground, so they are not able to rotate, no rotation. Rotation is equal to 0. Only joint B can rotate. So 1 rotational degree of freedom. In order to find the translational degree of freedom, we should convert all these to the pure hinge. If I convert to the pure hinge, this system is stable already. I don't need to add extra member. So the translational degree of freedom is equal to 0. In that case, total degree of freedom for this system will be only 1 degree. The only unknown we have, it is theta B. Let's see how we can find MA. MAB will be equal to M fix AB plus 2ei over L minus 2 theta A minus theta B. Because delta is equal to 0, we will not apply in the formula. This is MAB. How about MBA? MBA will be M fixed BA plus 2EI over L minus 2 theta B minus theta A. MBC. MBC will be M fixed BC plus 2EI over L minus 2 theta B minus theta C, that is MBC. MBD will be M fixed BD plus 2EI over L minus 2 theta B minus theta D. We know theta D is equal to 0. We know theta C is equal to 0. We know theta A is equal to 0. So from here, MBA, it will be M fixed BA minus 4EI over L theta B. MBC will be M fixed BC minus 4EI over L theta B. MBD will be M fixed BD because there is no load here. So that is equal to 0 plus minus 4EI theta B over L. This will be M fix AB. Theta A is equal to 0 minus 2EI theta B over L. Now, if we look at the equilibrium of joint B is rigid joint. The summation of moment in this joint M, BC, M, BA, M, BD should be equal to 0 in order to have that joint in equilibrium. So I should write MBA plus MBC plus MBD is equal to 0. Let's write it MBA plus MBC plus MBD is equal to 0. So we have one equation, one unknown. Our unknown is theta B. I can plug there and I will find theta B. Before doing that, I should find M fixed. M fixed, if we have two N fixed and concentrated load at midspan, the magnitude of each one will be PL over 8, PL over 8. So for MBA, this one, M fixed BA will be negative PL over 8 because it is clockwise, negative PL over 8 minus 4 EI theta B over L. You see that. M fixed BC. M fixed BC will be positive PL over 8 because it is counterclockwise, minus 4EI theta B over L. MBT will be minus 4EI theta B over L is equal to 0. PL over 8 and PL over 8, they will cancel each other. From here you will find theta B is equal to 0. Theta B is equal to 0, we will plug here. Theta B is equal to 0, so MAB will be equal to M fixed AB, and M fixed AB it is PL over 8. PL over 8 counterclockwise. As an external moment, counterclockwise moment, we assume it is positive if it is counterclockwise. But if we want to draw moment diagram, pay attention. If we draw moment diagram, if we rotate point A counterclockwise, it will produce compression. It will produce compression in the A. So it is negative moment. So it is negative moment. If I draw moment diagram, it is negative moment. But if I want to show as external moment, because I assume counterclockwise is positive, I will call it positive PL over 8. Positive PL over 8 means it is counterclockwise at point A. Negative moment at A means it will create compression underneath of this beam at point A. That is the difference. So there is a difference between external moment, positive and negative, and internal moment. Once in moment diagram I show negative, means it creates compression underneath of the beam. If I show positive, it means it creates tension underneath of the beam. But about direction, external moment, once I show counterclockwise, I call it positive. Once I'm taking moment clockwise, I call it negative. Thank you so much for watching this lecture. See you next session. Bye.